Oh, it came off, sorry. Is that better? Yeah. Okay, so thank you for organizing the conference, and I want to say that I am focusing in issues in philosophy of science that are a little different than some of what we've heard. My main interests are in epistemology and how we've acquired knowledge in science and how to characterize that knowledge. And I've often looked at historical cases, which you'll see reflected in the talk. And in cases of historical history of science, I have some advantage on the actors given several hundred years in some cases of subsequent wisdom. So in looking at contemporary science, I'm all too aware that I don't have any advantage, and I hope that my inevitable mistakes about the state of contemporary cosmology and the state of inflation are offset, but by what I hope is an interesting different perspective on some of the questions, in particular questions like those that arose in yesterday's panel discussion in the afternoon. So let me start by introducing a few things that are probably familiar to everyone here. I'm going to be talking about testing the inflationary paradigm, and what I mean by that is a pair of claims. The first is that various features of the early universe, such as its overall flatness, uniformity, spectrum of density perturbations, are consequences of a transient phase of accelerated expansion, which is characterized by the second derivative of the scale factor being greater than 0. And inflationary models specify what the physical source is for this transient phase of accelerated expansion. Now, there's a huge, enormous variety of inflationary models that have been explored over the 30 years that the theory has been studied. I'll be focusing on particularly simple models where you have the source is a scalar field displaced from the true minimum of an effective potential. And in such a state, the scalar field will contribute to the stress energy tensor, assuming that derivative terms are negligible as an effective cosmological constant term, leading to a de Sitter-like phase of expansion. So this is a kind of quick textbook rendition of the initial motivations for inflation that you'll still see in a lot of cases that was presented by Alan Guth in his seminal paper as the motivations for inflation. That inflation was to be accepted because it solved two initial conditions or fine-tuning problems, which are the flatness and horizon problem. So I'm sure you've all seen this, so I'll go through it very quickly. Guth, of course, was also concerned about the monopole problem, but let me set that aside for this discussion. The flatness problem refers to the fact that under standard FLRW dynamics, the density parameter evolves rapidly away from 1. So the fact that we still observe omega to be close to 1 is surprising and puts a very strong constraint on what the earliest, very early value of omega would have to be. So it looks like it has to be very finely tuned in the early universe. Secondly, there's the horizon problem, which is a reflection of the causal structure of standard FLRW spacetimes, namely that if we look at points on the surface of last scattering, the past light cones from those points in the standard cosmological model will not overlap. And so it's surprising that the conditions in those different regions are so uniform. Now, there's been a lot of discussion, so the sense in which inflation solves these is fairly straightforward. The horizon distance will be stretched by a factor, so given sufficient e-foldings of inflation, the horizon distance will stretch so that the past light cones of points on the surface of last scattering do overlap. And the dynamical behavior of omega is reversed during inflationary expansion, and so it's driven towards 1. And so the picture is that for what looks like more plausible initial conditions, so for a wide range of initial conditions, you'll get something like the starting point for subsequent evolution in the standard cosmological model. Now, this case for inflation, if this were the only motivation for inflation, I think there are some really important problems with this. So we've seen earlier discussions in this conference. So John Barrow, for example, said very explicitly, what do we mean by probabilities in this context? And here I think it's a quite pressing issue. To echo something that David Wallace mentioned and something that's come up in earlier discussions, the picture that seems to underwrite this case is as if you're choosing a point from a phase space using Lebesgue measure, and you're defining the phase space as a space of possible solutions of Einstein's field equations, and then it seems surprising that you would get the exact FLRW models or the flat models. But it's not clear that that's the appropriate picture to have for considering initial conditions of the universe. There's just deep problems with understanding what we mean by probabilities in that context, or choosing a particular measure by which to introduce those probabilities. It seems that that kind of picture is more like a hypothesis about how to assign probabilities that doesn't get support in the usual ways that assignments of probabilities do in other contexts like statistical mechanics. Secondly, there's a kind of hoist by your own petard kind of objection, which is that by its own logic, the inflationary solution doesn't actually achieve what it's designed to do. And this is an objection that's been pressed by Penrose in various places, most recently in his book. Now, I think these are important objections. I'm not going to focus on this discussion today. Some of the people in the room have already contributed a great deal to that discussion. But I think in terms of the evolution of the field, by which I mean the sociological evolution of the field of cosmology, not of the scalar field, something else has been much more important. And this is captured very nicely in this quote from Andrew Little and David Lith in their textbook of 2000, in which they basically, in the first few pages, set aside the standard kind of motivation for inflationary cosmology and say that's actually not what's exciting about inflation. What's exciting about inflation is the other feature of the theory, which is that it gives you a prediction for formation of density perturbations in the early universe that reflect features of the scalar field and its evolution. And I think this actually captures a fairly widespread shift in the field towards thinking of inflation as primarily a theory of structure formation. And so if you also look at how it's been tested against competing theories, this is the part of inflation that's really been the workhorse. So in the 1990s, there are various people who are pursuing theories of topological defect formation as an alternative way of creating structure in the early universe. Those were tested against this aspect of inflation, the way that it produces a particular spectrum of density perturbations. And subsequently, other alternatives are usually trying to capture this aspect of inflation, namely trying to give us an account of structure formation or of the initial density perturbations. So I think in terms of the evolution of the field, this has really become the most important part of the theory empirically. And I want to then phrase a question quite generally about how to assess theories and see some strategies that have been used in other cases and see how they apply to inflation. So I think the very general question we're faced with is something like the following. Given a theory T, construct models with observations used to constrain the parameters in the model. So there's some domain of observations that you're trying to model. You use features of those observations to then constrain parameters appearing in the model. And what features of models that are compatible with observations will lend credence to the background theory T? In what cases do the models convince you that you've gotten the right description of the systems or the right description of the systematic physical dependencies that are important in understanding the physics at hand? Now, I think there's a few challenges to just taking the fact that you're able to fit the data as sufficient to give you credence in the theory. And a standard worry here is that we want to distinguish between T merely accommodating the data, just giving you a curve fit because T might have enough flexibility to do so, instead of identifying the correct physics or the correct physical dependencies that are relevant to the domain in question. And secondly, how stringently is T tested in further research based on accepting it as giving you the correct description? And I think historically we can see some very compelling responses to these kinds of questions. The challenges for inflation I'll highlight are the following. One common complaint, and this is a phrase due to Michael Turner, is that inflation throughout this period has been a paradigm without a theory in the sense that there hasn't been a standard canonical model. And so it seems to be quite flexible in allowing a variety of models. So this first challenge, I think, is particularly pressing. Secondly, there's a question about how natural or plausible is the best fit model. That's something I'm going to come back to. This is something that I think is really important in some very recent debates about what models of inflation are best fit by the Planck data. And finally, with regard to how stringently is T tested in further research, I'm going to ask how much of the details of inflation have been probed by further research in the field. So in outline then, I want to say something briefly about the kinds of strategies that I think have been used to answer these challenges in other areas where I think they've been used quite effectively. Then I'll turn to looking at inflation, and then I'll say something briefly about this last question about how plausible a certain model is, which ties in with debates about initial conditions again, and also lead to debates about eternal inflation, which I'll probably have less to say about depending on how much time I have. So here's my first golden oldie. It's one of these tunes that I'm sure you've heard before and know and love. But this is a selection of a text. I'm sorry the text hasn't come through in very high resolution, but this is from Perrin's book on atoms in 1913. And this is a case for the atomic hypothesis based on 13 different phenomena that allow you to put constraints on the value of Avogadro's number. And Perrin argues, our wonder is aroused at the very remarkable agreement found between values derived from the consideration of such widely different phenomena, seeing that not only is the same magnitude obtained by each method when the conditions under which it is applied are varied as much as possible, but that the numbers thus established also agree among themselves without discrepancy for all the methods employed, the real existence of the molecule is given a probability bordering on certainty. So this has been a target of discussion among philosophers who are debating realism and the extent to which we should be committed to unobserved entities such as atoms and molecules. And they've rightly identified Perrin's argument as a quite impressive argument and tried to clarify the structure. So schematically, we have a variety of measurable quantities for each of the 13 cases, all of which are related to the value of n if the atomic hypothesis is correct. And Perrin's conclusion, of course, is that measurements, all these different measurements are agreeing measurements of the same quantity, and that supports the atomic hypothesis. Now, I think the importance, or one possible limitation of this kind of argument is how do we assess the probability of agreeing measurements if the atomic hypothesis is false? Is there another hypothesis that would give us similar connections that would be a competing hypothesis with the atomic hypothesis? And here I think the fact that these measurements are measurements of such a wide variety of quite distinctive phenomena gives us a lot of reason to say that there will be a very low probability of agreeing measurements if in fact the atomic hypothesis is false. In other words, it's only the systematic unification provided by the atomic hypothesis that relates phenomena as distinct as the color of the sky and Brownian motion. Right? So it's only once you have the atomic hypothesis on board that you have a connection between those types of phenomena. Recently, my colleague Wayne Mervold has given an analysis of this kind of reasoning where he does this in Bayesian terms. I'm just going to mention this briefly. It, I think, really underwrites the kind of schematic argument that I gave. He defines the unification of a theory as the degree to which the theory establishes a connection between apparently independent phenomena, and it renders them informationally relevant in the sense the log here isn't particularly important, but the important point is that the two things are informationally relevant to each other if they raise conditional probabilities, one with respect to the other. And then the amount of unification with respect to a t is a measure of how much it raises the relevance. In other words, how much does it tie these distinctive phenomena together? And in Mervold's analysis, then, this isn't something that's put into assessing the priors or anything like this. This is something that is directly part of the conformational boost under Bayes' theorem that's delivered to a theory. If it's more unifying, there's a greater boost than you'd get independently from the two separate phenomena. Okay, so that's the first example of a schematic argument that gives you confidence that your initial model is not just a curve fit. Here's a second example, the second golden oldie, which has already been played earlier in the conference, but this is the discrepancies in the motion of Uranus that were measured following its discovery up until around 1840, and you can see that the discrepancies get up to about 120 seconds of arc. And these are discrepancies that are left over after the other perturbative effects of Jupiter and Saturn are taken into account. So this is something that is only defined relative to the existing knowledge about the motion of objects in the solar system, and there's a residual discrepancy. And in this case, obviously, you can go and look and find the thing that's the source of that discrepancy. It's about as robust a source of the discrepancy as you can imagine. But in general, what the schematic version of this argument is that we have a calculation from a theory with a number of details included that gives us, in this case, a description of the motion of objects in the solar system, and we have a comparison of that with observations. Now, a discrepancy emerges with a clear signature, and then we're able to identify a robust physical source that's compatible with the underlying theory. There's no obviously, introducing a new planet was something that had no conflict with Newton's theory of gravitation. And over the 200 to 300 years of research in celestial mechanics, this kind of process was repeated over and over again, and you acquire a body of knowledge of the physical details that make a difference in the motion of objects in the solar system that's all built up on the basis of Newtonian gravity. Now, in this case, it's particularly easy to identify a source of the discrepancy. In other cases, it's more subtle. So the understanding of the great inequality in the motion of Jupiter and Saturn actually required an understanding of how the eccentricities of their orbits contributed to the perturbative effects of the planets on each other, and so on. So it isn't always as clean as just finding a new entity. It's sometimes recognizing physical details that make a difference that were not readily apparent before. So my claim is then that these are two strategies for meeting the challenges that I identified earlier, namely that the overdetermination of the model from independent phenomena makes it convincing that this isn't just a curve fit, that this isn't just accommodating the data with something that's a flexible theory. And secondly, successful identification of robust physical sources for discrepancies repeated over and over, and the theory becomes a constitutive part of that research, really also provides an answer to the second challenge. So I think this is a matter of degree, but I think you can make a plausible case that theories meeting these challenges so effectively should be considered permanent in the sense that successor theories are required to recover the theory and the reasoning based on it as approximately true within a restricted domain. So I think there's a lot of care that's required to formulate this a bit more precisely. This is a part of the debates about continuity through theory change that a lot of philosophers and historians have been interested in. But I think that if you look at theories that have met the challenges as effectively as atomic hypothesis, Newtonian gravity, and several other cases, it's hard to imagine that those would not be recovered in some limiting sense in future theories. So again, that was a sort of historical prologue illustrating different types of argument, which I think have been quite important in the historical development of physics. And I want to turn to considering the case of inflation with these two examples in mind. So we can ask then, is it possible to apply similar strategies? Can we overdetermine the properties of the inflaton field from observations? Can we so tightly constrain it that we are convinced that it's not merely accommodating the data? And is it possible to refine the basic account of inflation and get a much more detailed account of the physics underlying inflation? And I think in the case of inflation, it's much more difficult currently to meet these challenges. So let me briefly give a sketch of structure formation in inflation. This was described in more detail by Professor Sudarsky earlier. So this is just a very brief sketch, but the characteristic feature of evolution during the inflationary phase is that the Hubble radius and the scale and a co-moving scale will cross and then recross during and after inflation. So it's called horizon exit and reentry, and it just reflects the fact that the Hubble radius is constant during the inflationary phase, which you can see, well, you can see in these illustrations. You can't actually read the axes, but they're log time and log physical scale. And then after the inflationary phase is over, the Hubble radius is proportional to the square of the scale factor, and so then it crosses back in through the Hubble radius, a given physical scale. And so then, again, this is a standard account, and Professor Sudarsky raised the issue of how to think of this freeze out in more detailed terms, because it's actually a quantum to classical transition. But the idea is that modes of a field that is initially in a quantum field, usually assumed to be in a vacuum state, then evolve in such a way that when they're initially adiabatic, and then they are overdamped outside the horizon. So the modes freeze out at horizon crossing, then come back in as classical perturbations, which then seed the density perturbations that we see in the CMB sky. Although there's a lot of subsequent physics, as previous speakers have mentioned, that lead to the particular coherent oscillations that were observed by WMAP. Now, this connection between the evolution during inflation and the properties of the perturbation spectrum is reflected in the simplest case, if you assume that it's a Gaussian spectrum, in terms of a set of relationships between a number of quantities characterizing different aspects of the perturbation spectrum. So just as in the case of the atomic hypothesis, we then have a number of law-like relationships introduced to the theory between these quantities, which are measurable quantities that we can see in the CMB. And so in particular, and I think we saw some detail about this in the very first talk, relating how these quantities reflect the effective potentialist derivatives. Usually, we're assuming that we have slow roll inflation, which is the simplest case. So then we have a system of law-like relationships, and we can ask whether we can use the observations of the CMB to then constrain the underlying model in much the way that Perrin used different phenomena to constrain the atomic hypothesis. So the problem with, and I should emphasize throughout, one thing that's important is that, of course, inflation is able to accommodate all the data, unlike other ideas that have been proposed for accounting for the formation of structure in the early universe. And these observations constrain the potentialist derivatives, also the energy scale and the length of the inflationary phase. There's a part of inflation that I'm not going to discuss in detail, which constrains a different part of the effective potential, which is responsible for reheating, which is a phase that occurs after the inflationary expansion. But one thing that's remarkably absent in terms of contemporary model building are strong constraints from particle physics. And this is reflected in the huge plethora of different inflationary models that have been proposed, numbering in the hundreds, which all are in some sense motivated by particle physics, but the energy scales of inflation are weakly constrained by current particle physics. So we do have inflationary models meeting these constraints, but in fact we have many of them. And so there's a recent work called Encyclopedia Inflationaris, which has a catalog of 193 of the simplest models. These are all single field, slow roll inflationary models. And this is by Martin and a group who created this catalog. Again, there are other more complicated models. This is by no means the full list of inflationary models. And of those 9 models are still favored by the Planck data. So it's an achievement that there are models compatible with the data, but they're certainly not over-constrained by the current data. It's certainly not analogous to the case of the atomic hypothesis. So in addition, the fact that there's no canonical model means that there's insufficient basis for taking a particular discrepancy between what a given model tells you and what you see in the CMB sky as a source of information for probing the further physical details of inflation, as opposed to just taking it as evidence that you should have chosen a different initial model to begin with. So there isn't the kind of constraint on the theory that allows you to further probe the details of inflation, taking advantage of discrepancies. Now, I want to say something about what I see as the main source of these challenges, and this is in response to some of the worries raised by George Ellis. It isn't obvious to me that the uniqueness of the universe per se is directly responsible for these challenges. The two strategies I've formulated, and I should have said earlier, I don't mean these to be the only strategies available, but these seem to be the ones that are available in the context of cosmology, because they don't depend directly on experimentally manipulating the system in question, and they don't depend directly on multiplicity of instances. So both the strategies could be employed in cosmology, and it's just a contingent matter of fact that we don't have the kind of accessibility to the relevant energy scales and to the details of inflation that we would need to fully exploit these strategies. So what we would need in order to adopt either of these strategies is independent ways of probing the relevant physics, observationally or experimentally, or access to phenomena with increasing accuracy and detail, with the ability to build up systematically a description of the phenomena, taking account of discrepancies and robustly identifying sources of those discrepancies. And it doesn't seem like either of those turns on the uniqueness, it's a matter of the accessibility. Now, I want to come back to one of the other questions I raised at the start, because there's a recent debate in response to the Planck 2013 data, which I think is focused on the question of, give me a best fit model. How natural or plausible is that? With two different aspects of this question. Is the shape of a particular effective potential plausible? And are there plausible ways in which inflation could get started, given that potential? So this is the debate between Anna Ias, Paul Steinhardt, and Abraham Loeb, who've been quite critical, saying that the best fit models following Planck 2013 require an unusual shape. They call it a finely tuned plateau potential, and they've criticized the initial conditions that this seems to require. Guth, Kaiser, Nomura, and Linde have replied to this and have argued that, in fact, the plateau potentials are not particularly unlikely, and that they can be augmented by more complicated potentials leading to a plateau potential at late times. And they've suggested various plausible scenarios leading to a pre-inflationary state. Now, I think these kinds of debates, like the debates about the initial case for inflation, are really difficult to assess, because they really turn on assessments of probability or plausibility for different aspects of the initial conditions or features of inflation. So I think unless we have a particular particle physics model or theories in mind that allow us to assess a given potential or effective potential as likely or unlikely, it's not clear exactly what basis these sorts of judgments have. Or at least I think the real issue is, what are the reasons for these judgments of the plausibility or not of particular effective potentials? And that needs to be brought out more into the open. But both the critics of inflation and the defenders agree that there's one feature of these plateau-like potentials that is striking, which is that they both lead to eternal inflation. And in some sense, for the critics, this is particularly problematic because they argue that eternal inflation leads to a scenario which makes no predictions at all, given that there's no well-defined measure. The advocates of inflation argue instead that eternal inflation plus anthropic selection, in fact, answers some of these worries about the particular form of the effective potential in the appropriate pre-inflationary state. Now, I think I'm running out of time, so I had a further comment on eternal inflation, but I'm just going to skip that. The point is, in either of these, the Guth, Kaiser, and Nomura also acknowledged that the question of extracting predictions from inflation, if it's acknowledged to be eternal inflation, is difficult. They acknowledge that there's no solution to the measure problem. So in both of these cases, the fact that the current models lead to eternal inflation is seen as a problem for predictivity, which you should take as an additional problem compared to the ones I was discussing earlier. So let me just skip this discussion. So I want to close then by emphasizing what I see as challenges for early universe cosmology, again, from an outsider's perspective, somebody looking at different strategies that are pursued in other areas of physics. And what's striking looking at the development of early universe cosmology is that despite the vast increase in data, or vast increase in knowledge of the cosmos and its evolution, is the difficulty in particular for early universe cosmology in constraining and refining inflationary models. And that seems to be due to just contingent facts about the energy scale of inflation that mean that we don't have access to those scales. And I think there's an interesting question then, which I'll pose hopefully somewhat provocatively. And again, this is something that was discussed in the panel session yesterday. Is it a plausible goal to establish early universe cosmology as a permanent part of physical theory, in the sense of establishing the kind of strong evidence that we have for things like the atomic hypothesis and Newtonian gravity, which seems to make a convincing case that any successor theory should at least recover those ideas in some appropriate limiting form? Thank you.
Questions?
Thanks. Ofer Lahav, you've made a number of interesting points about the observational approach to the subject. Another point is, and I wonder what you think about it, is what is the stopping criterion? When do we decide to stop? So to give a simple example, the curvature of the universe. We know it's zero, but it's not exactly zero. It's zero to within, say, 1%. Why is it that most people think it's no longer interesting? It's probably because it's the answer most people like. Had it been a different answer, plus minus 1%, people might have liked to explore it further. So I wonder how you see that aspect of when to stop, when we decide it's good enough. And it's of interest all the way from, what a PhD student has to decide about to a funding agency. Thanks.
Right. That's a really hard question. I don't know. I don't want to be seen as advocating a kind of quietist proposal that you should just stop looking. My thought is rather that in some cases the practical limitations are so extreme that nobody's going to be funding a particle accelerator to get to the kinds of energy scales where you could see interactions with the inflaton field, right? So that's a more extreme case than the kind of case you're wondering about, where I think you probably do have to make assessments of what's the likelihood of being able to see something given the sort of scope of current ideas under discussion, and also consider the feasibility of the observational studies. But and you mentioned people use figure of merit calculations and things like that to try to make that assessment, and that seems, I don't think I have anything revealing to add to that kind of discussion.
Hi, Casey McCoy. I was just thinking about your the example of the atomic hypothesis, and with the overdetermination of Avogadro's number, right? Yeah. So what I was thinking is there seems to be more than one thing going on there, though. There's the overdetermination that we see of Avogadro's number, but what also seemed important in the way you set things up is that there weren't other alternatives besides the atomic hypothesis. You said there weren't any other plausible alternatives, and that's the reason that we should.
Well, I didn't mean to. So I didn't mean to say. So what I meant to say is that if you're trying to assess, so to put it in Bayesian terms, the unification will give you an extra boost compared to a non-unified theory. But if you're doing a contrastive assessment and you have two theories that both introduce systematic relations among these quantities, then yeah, that other theory will also receive a boost under unification. The claim I did make is that the variety of different kinds of phenomena that were connected by these systematic relations makes it seem quite implausible that just assuming that the atomic hypothesis is false, that there would be systematic relations among these, right? So that is a claim about, I'm saying, it's unlikely that there will be a competing theory that ties the phenomena together in exactly the way the atomic hypothesis does. And that's a matter of degree. It depends to some extent on the variety of phenomena that are under consideration and the degree to which they're quite distinctive domains.
Joel Premack. There's a question that I'm kind of interested in as a practitioner, having written some of the early papers on inflation. Back in the old days, before Kobe, we didn't know what the fluctuation spectrum looked like. And the inflationary plus cold dark matter models made very distinctive predictions that looked very much like the result that we're all familiar with, the curve with all the wiggles. So, question, does it matter that this was a prediction and then lots of data came in, literally many, many thousands of independent data points that beautifully fit with just a little bit of adjustment of parameters, the predictions that were made? That, I think, for the practitioners is one of the strong reasons why we take inflation seriously. A couple of other quick points. The basic idea that you say, or you quoted Leith and Little as saying, is no longer very interesting, namely the uniformity of the cosmic microwave background temperature. That's really the same story as structure formation. Structure formation requires a huge amount of acausal information to be put in. That's the whole essence of structure formation. So, yeah, the uniformity of the temperature is just one aspect, but it's the same idea, just carried out on many, many different scales. And then a final point, we're nowhere near the end of the story. We haven't yet seen the Planck polarization data. They promised to release it later this year. And of course, there's going to be these great ground-based experiments like BICEP2. And those are going to tell us a great deal more. And this debate that you talked about is going to seem, it already seems like ancient history, because it doesn't take any of that into account. So it may very well be that we're going to learn a lot more about the nature of inflation. It's been known for a long time that if you want to reconstruct the inflationary potential, you need to know the energy scale of inflation. And the way we have to learn that, if we're lucky, is going to be by measuring the gravity waves.
Right. So let me take your middle question first. So I think one thing that Little and Lith don't say, but I think is quite plausible, is just to assess to what extent the flatness and uniformity provide constraints on the inflaton potential. And you're right that flatness and uniformity will both constrain the overall length of the phase of inflation. So in that sense, it's part of the same process, but it's not as revealing about the nature of the inflaton potential as the details about the scalar and tensor perturbations. So I think in that sense, they think of the theory of initial conditions aspect of inflation as not being particularly revealing, whereas they do think the account of structure formation reveals more about the details of the evolution during the inflationary phase. Regarding your first point, there's a general debate about whether accommodation or prediction should be given particular weight. I don't doubt that it's often given quite important psychological weight. So when you actually, so I guess the first point is that there was an initial discussion of the amplitude of the overall amplitude of the fluctuations, which then led to a particular class of inflationary models with a flatter potential, right? So once you fix the amplitude, using data to constrain the amplitude, then yeah, you get a lot of results out of the inflationary models, and you're right, that was before Kobe. But I think there's a general philosophical question about whether the relation between theory and evidence should be conceived of just as a question of the logical or structural relation between those two, in which case the question of whether the predictions were discovered first or not is actually not relevant to the question of how well the evidence constrains the underlying model. That's part of a big debate. And yes, of course, there are further ways of testing the gravitational wave, the tensor spectrum. That will give you a model-independent measure of the energy scale of inflation. But I'll also test the consistency relations that result from the way these perturbations are produced. But it's, I mean, I think there's an open question whether that will be seen as convincing in terms of degree of constraints that you've imposed on the inflationary model as other cases in physics where we have much more over-constrained models for our theories. So I think it's a matter of degree.
Cormac O'Rafferty from Ireland. I'll be brief. I had a similar question, but let's just add the twist that, as you all know, I mean, the thing about structure formation, if I remember correctly, is it came as a bonus. You won't find it in Alan Goose's original paper. So it's even more impressive that you have this theory which is put forward to explain certain things, and next thing, structure formation, probably one of the very first even attempts to have a model for it, appears out of absolutely nowhere. So certainly one feels intuitively that that's very impressive, that it's not some sort of a put-up, what's the word, a convoluted job to explain something. Quite the opposite, I would have thought. And the same with flatness, because after all, they were talking in those days, we always forget, they were talking about the theoretical paradox. They weren't talking about observational flatness. That came much later. So it's pretty impressive, isn't it? Have I got that right?
Well, so there were people who were interested in the study of density perturbations before Guth, Mukhanov in the Soviet Union. But you're right, it wasn't something that was part of Guth's original case in favor of inflation. It was at the Nuffield workshop and a year or two later that people first started systematically studying the prediction of density perturbations. But I think your question goes back to, so I think a lot of people think that prediction should be more valuable because the theorists won't be allowed to create something to fit data if they don't know the data, right? So in that sense, a prediction is seen as more valuable because it's a limit on the ingenuity of theorists. But I think from a different point of view, it's not clear that that should be given an extra boost in terms of assessing the theory. If you're really just asking, how well do the set of observed phenomena constrain the underlying model? That seems independent of exactly how it is that you arrived at the model. And so I think you can ask that kind of question without necessarily looking at the historical details of how the model arrived, even though that's important in a lot of ways.
Chris Weaver, Rutgers University. I waited for the mic this time. So I think the measure problem is a serious problem for eternal inflation. And so I find the argument from Steinhardt and others that standard inflationary theory implies eternal inflation sort of like a potential objection for standard lambda CDM. But I just wanted to point out that it looks to me as if, I'm not a physicist, but it looks to me as if the arguments on which Steinhardt and others depended in order to make the connection between standard inflation and eternal inflation depend upon an effective quantum field theoretic approach to the inflaton. Like they use quantum field theory to interpret, to understand the inflaton field. So Tom Banks gave us a picture, right, the holographic approach to inflation, which does not view the inflaton field as a quantum field, but as a classical field. And so it seems to me as if the holographic approach to inflation avoids the implication, standard inflation yields eternal inflation, and so perhaps avoids a measure problem.
If Tom Banks is here, I'll let him comment on that. I mean, I think there's alternatives that capture some aspects of inflation that avoid eternal inflation. So it sounds like if that's one of them, then yeah, that's, and they're certainly using quantum field theory in the description of the inflaton potential. So, but I think Tom maybe has left already, I don't, yeah.
Last question.
Brian Pitts. I'm wondering if anything useful has been said, or in your opinion could be said, about the measure problem if one relaxes normalization constraints on probabilities?
Well, I think you're dealing with non-normalized spaces in any case. I think everybody's assuming that the spaces aren't compact. So I'm not sure what you have in mind. I mean, I think the question currently is finding a way of introducing a measure that doesn't rely upon some extraneous structure that seems problematic, and also finding a measure that produces the right kind of predictions that you want eternal inflation to give. So I don't know that relaxing the kind of constraint you're, I think in effect that constraint is already relaxed, so.
Let's thank Chris again.